Picture this: vast stretches of space, so empty and dark that they defy everything we think we know about the universe. These are cosmic voids, regions where galaxies are almost non-existent, and the rules of physics seem to bend in ways we can barely comprehend. What if I told you that these voids, these seemingly empty spaces, hold some of the greatest mysteries of the cosmos? From unexplained movements of galaxies to strange signals that hint at forces beyond our understanding, cosmic voids are not just empty, they are gateways to the unknown. In this video, we're diving deep into 25 of the most baffling phenomena hidden within these cosmic voids. By the end, you'll see the universe in a way you never have before. So, what exactly are cosmic voids, and why do they leave scientists scratching their heads? Let's start with the basics. Cosmic voids are enormous regions of space where the density of matter is significantly lower than the rest of the universe. Think of them as the universe's empty rooms stretching for hundreds of millions of light years. But don't let their emptiness fool you. These voids are anything but simple. They challenge our understanding of dark energy, dark matter, and even the very fabric of space-time itself. Why do they exist? What secrets do they hold? And could they be the key to unlocking the mysteries of the cosmos? Stay with us as we explore these questions and more, uncovering the 25 most unexplained phenomena lurking in the cosmic web's voids. Now, let's turn our attention to the Boötes Void, a region of space so vast and empty that it has earned the nickname the Great Nothing. Stretching an astonishing 330 million light-years across, this void is one of the largest known structures in the universe. To put that into perspective, if you were to travel at the speed of light, it would take you more than 300 million years to cross it. That's how immense this cosmic emptiness truly is. The Boötes Void was first discovered in the 1980s when astronomers noticed a peculiar absence of galaxies in a specific patch of the night sky. Unlike most regions of the universe, which are teeming with galaxies, stars, and cosmic activity, this area was eerily quiet. In fact, it's estimated that the Boötes Void contains only about 60 galaxies, a staggeringly low number compared to the thousands you'd expect in a space of that size. So, what could explain such a vast emptiness? Scientists have proposed several theories, each more fascinating than the last. One possibility is that dark energy, the mysterious force driving the accelerated expansion of the universe, plays a role. Some researchers suggest that dark energy might be more concentrated in voids, pushing matter away and creating these enormous empty regions. Another intriguing theory involves the idea of alien megastructures. Could advanced civilizations have built something so massive that it blocks our view of galaxies within the void? While this idea is highly speculative, it's a reminder of how much we still don't know about the cosmos. The Boötes Void challenges our understanding of the universe in profound ways. It forces us to question how such vast regions of emptiness can exist and what they might reveal about the nature of dark energy, dark matter, and even the possibility of life beyond our own galaxy. As we continue to explore this cosmic mystery, one thing is certain. The Boötes Void is a reminder that the universe is full of surprises, and sometimes the most profound discoveries come from the places where we find nothing at all. Next, we'll explore another cosmic enigma, the Eridanus Supervoid, a massive cold spot in the cosmic microwave background that has left scientists equally puzzled. What could be causing this mysterious anomaly? Let's find out. Now, let's shift our gaze to another cosmic mystery that has left scientists scratching their heads, the Eridanus Supervoid. This colossal region of space is home to one of the most puzzling features in the universe, a massive cold spot in the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. The cosmic microwave background, or CMB, is essentially a snapshot of the universe when it was just 380,000 years old. It's a faint glow of radiation that fills the cosmos, and it's remarkably uniform, except for a few anomalies like the cold spot in the Eridanus Supervoid. This cold spot is a region where the temperature of the CMB is significantly lower than the surrounding areas, and it spans an area of the sky roughly 10 times the size of the full moon. So, what's causing this cold spot? One leading theory is that it's linked to the Eridanus Supervoid itself, a vast region of space that's unusually empty. Voids are part of the cosmic web, the large-scale structure of the universe that resembles a network of filaments and empty spaces. In this case, the Eridanus Supervoid is thought to be one of the largest voids ever discovered, stretching over 1 billion light-years across. Here's where it gets interesting. Some scientists believe that the cold spot could be a result of the void's emptiness. As light travels through a void, it loses energy due to the expansion of the universe, a phenomenon known as the integrated Sachs-Wolf effect. This could explain why the CMB appears colder in this region. However, not everyone is convinced. Critics argue that the Eridanus Supervoid might not be large enough or empty enough to fully account for the cold spot. Instead, they suggest that the cold spot could be a statistical fluke, a random fluctuation in the CMB that just happens to look like a void. Others have proposed even more exotic explanations, such as cosmic texture, a theoretical defect in the fabric of space-time, or even the remnants of a collision with another universe. The debate over the Eridanus Supervoid and its cold spot highlights just how much we still have to learn about the universe. Is it a true void, a cosmic anomaly, or something even stranger? Whatever the answer, this mysterious region challenges our understanding of the cosmic web and the forces that shape it. As we continue our journey through the unexplained phenomena of cosmic voids, we'll next explore the local void, a region of emptiness that's much closer to home, and one that might be shaping the motion of our own Milky Way galaxy. Now, let's turn our attention to a void that hits closer to home literally. The local void is a vast, empty region of space that surrounds our very own Milky Way galaxy. Unlike the distant Boötes Void or the enigmatic Eridanus Supervoid, the local void is right in our cosmic backyard, and its influence is far from negligible. The local void is a sprawling expanse of emptiness, stretching over 150 million light-years across. But what makes it particularly fascinating is its proximity to us. Our Milky Way galaxy, along with its neighboring galaxies, sits on the edge of this void, almost as if we're perched on the rim of a giant cosmic crater. So, how does this emptiness affect us? One of the most intriguing ways is through its impact on the motion of galaxies. You see, galaxies aren't just floating aimlessly in space, they're constantly moving, pulled by the gravitational forces of nearby matter. But in a region as empty as the local void, there's very little matter to exert that gravitational pull. This creates a kind of imbalance, a gravitational push that influences how galaxies, including our own, move through space. Scientists have observed that the Milky Way and its neighbors are being pushed away from the local void, as if the void itself is repelling them. This motion, known as the local void effect, challenges our understanding of how galaxies move and interact on large scales. It suggests that voids aren't just passive empty spaces, they're active players in the cosmic dance, shaping the trajectories of galaxies in ways we're only beginning to understand. But the local void doesn't just affect motion, it also raises questions about the structure of the universe itself. Why is this region so empty? Is it a natural consequence of the cosmic web's formation, or is there something more unusual at play? Some researchers have even speculated that the local void could be a remnant of an earlier phase of the universe, a relic from a time when the cosmos looked very different. What's clear is that the local void is more than just a blank spot on the cosmic map. It's a dynamic region that challenges our assumptions about the universe's structure and evolution. As we continue to study it, we may uncover clues not just about our own galaxy's journey, but about the forces that shape the cosmos as a whole. Next, we'll explore another mysterious void, the KBC void, and how its immense size is sparking debates about the expansion rate of the universe. Stay tuned as we dive deeper into the enigmas of cosmic voids. Now, let's shift our gaze to another colossal void that's stirring up quite a debate in the world of cosmology, the KBC void. Named after its discoverers, Keenan, Barger, and Cowie, this void is the largest known local void in our cosmic neighborhood, stretching an astonishing 1 billion light-years across. To put that into perspective, it's so vast that it makes the local void we just discussed seem almost modest in comparison. The KBC void isn't just remarkable for its size, it's also at the center of a heated scientific debate about one of the most fundamental aspects of our universe, the rate at which it's expanding. This rate is measured by what's known as the Hubble constant, a value that tells us how fast galaxies are moving away from each other as the universe grows. But here's the catch: different methods of measuring the Hubble constant have been giving us conflicting results, and the KBC void might hold the key to resolving this cosmic puzzle. How does a void factor into this? Well, the KBC void's immense emptiness could be influencing the way we measure distances and speeds in the universe. When light travels through such a vast, low-density region, it behaves differently than it would in a denser part of space. This could skew our observations, making galaxies appear farther away or moving faster than they actually are. Some scientists argue that the KBC void's presence might explain why certain measurements of the Hubble constant don't align, suggesting that our understanding of cosmic expansion might need a rethink. But the implications don't stop there. The KBC void also challenges our assumptions about the uniformity of the universe. According to the cosmological principle, the universe should look roughly the same in all directions on large scales. Yet, the existence of such a massive void raises questions about whether this principle holds true. Could the KBC void be evidence of a more uneven cosmic structure than we've imagined? As researchers continue to study this enigmatic void, they're not just exploring its impact on the Hubble constant, they're also probing deeper questions about the nature of the universe itself. Is the KBC void a rare anomaly, or is it a sign that our cosmic models need updating? Whatever the answer, one thing is certain: this void is more than just an empty space. It's a window into some of the most profound mysteries of the cosmos. Next, we'll delve into another cosmic enigma: the mysterious movement of galaxy clusters known as the dark flow. What could be pulling these clusters in a specific direction, and what does it reveal about the unseen forces shaping our universe? Stay with us as we uncover the secrets of this intriguing phenomenon. Now, let's turn our attention to one of the most baffling phenomena in the cosmos, the dark flow. Imagine this: galaxy clusters, some of the largest structures in the universe, are all moving in the same direction, as if being pulled by an unseen force. This mysterious motion, detected through careful observations of the cosmic microwave background radiation, has left scientists scratching their heads. What could possibly be causing such a coordinated movement across vast distances? The dark flow was first discovered in 2008, when researchers noticed that hundreds of galaxy clusters were streaming toward a specific region of space at incredible speeds, up to several million miles per hour. This movement defies the expected behavior of galaxies, which should be moving apart due to the expansion of the universe. Instead, these clusters seem to be drawn toward something beyond the edge of what we can observe. So, what's behind this strange phenomenon? One leading theory suggests that the dark flow could be caused by the gravitational pull of a massive structure lying outside our observable universe. This structure, often referred to as a supervoid or supercluster, would have to be unimaginably large and dense to exert such a powerful influence. Some scientists speculate that it could be a remnant from the early universe, a relic of cosmic inflation that left behind an uneven distribution of matter. Another intriguing possibility is that the dark flow might be evidence of a multiverse. If our universe is just one of many in a vast cosmic landscape, the gravitational tug of a neighboring universe could explain why galaxy clusters are being pulled in a specific direction. While this idea is highly speculative, it opens up fascinating questions about the nature of reality and what lies beyond the boundaries of our observable universe. Of course, not everyone agrees on the cause of the dark flow. Some researchers argue that it could be a result of measurement errors or anomalies in the data. Others propose that it might be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. Could dark energy be acting unevenly, creating a kind of cosmic current that's pulling galaxies along with it? As scientists continue to investigate the dark flow, they're not just exploring the motion of galaxy clusters, they're probing the very fabric of the cosmos. This phenomenon challenges our understanding of gravity, the large-scale structure of the universe, and even the limits of what we can observe. Whether it's a massive unseen structure, a neighboring universe, or something entirely new, the dark flow reminds us that the universe is full of surprises. Next, we'll dive into another cosmic mystery, the missing baryon problem. Where is half the normal matter in the universe hiding, and could cosmic voids hold the key to solving this puzzle? Stay tuned as we unravel this enigma. Now, let's shift our focus to one of the most puzzling questions in modern astrophysics, the missing baryon problem. Baryons are the building blocks of ordinary matter, the stuff that makes up stars, planets, and even us. Yet, when scientists tally up all the baryons in the universe, they find that about half of them are unaccounted for. Where could this missing matter be hiding, and what role might cosmic voids play in solving this mystery? To understand the scale of this problem, let's break it down. Based on observations of the early universe, scientists have calculated how much baryonic matter should exist today. But when they look around, they only find about half of that amount. The rest seems to have vanished without a trace. This discrepancy has led to decades of research and speculation, with cosmic voids emerging as a potential hiding place for this elusive matter. Cosmic voids, those vast, empty regions of space, might seem like unlikely candidates for harboring missing matter. After all, they're defined by their lack of galaxies and other visible structures. However, recent studies suggest that these voids could be filled with diffuse gas-hot, thin clouds of baryonic matter that are incredibly difficult to detect. This gas, often referred to as the warm-hot intergalactic medium, or WIM, might be the key to solving the missing baryon problem. The challenge lies in detecting this gas. Unlike stars or galaxies, the WIM doesn't emit much light, making it nearly invisible to traditional telescopes. Instead, scientists rely on indirect methods, such as observing how the gas absorbs light from distant quasars or using X-ray telescopes to detect its faint glow. These observations have revealed that the WIM could account for a significant portion of the missing baryons, especially in the low-density environments of cosmic voids. But why would baryons accumulate in voids? One theory suggests that as the universe expanded, matter was pushed into the filaments of the cosmic web, leaving behind vast, empty regions. Over time, some of this matter may have cooled and settled into the voids, forming the WIM. Another possibility is that the gravitational pull of dark matter in the cosmic web could have drawn baryons into these empty regions, creating a reservoir of hidden matter. The implications of solving the missing baryon problem are profound. Not only would it fill a critical gap in our understanding of the universe's composition, but it could also shed light on the role of cosmic voids in shaping the large-scale structure of the cosmos. By studying these voids, scientists hope to piece together the full story of how matter is distributed across the universe and how it has evolved over billions of years. As we continue to explore the mysteries of cosmic voids, the missing baryon problem serves as a reminder of how much we still have to learn about the universe. These vast, empty regions might hold the answers to some of the most fundamental questions in astrophysics, from the nature of dark matter to the origins of the cosmic web. And as we uncover more about these enigmatic spaces, we move closer to solving one of the greatest puzzles in modern science. Next, we'll explore another fascinating anomaly, the void galaxy anomaly. Why do galaxies in voids often have unusual properties, and what can they tell us about the evolution of the universe? Stay with us as we dive deeper into this cosmic mystery. Now, let's turn our attention to a curious feature of cosmic voids, the void galaxy anomaly. Galaxies found within these vast, empty regions often exhibit properties that set them apart from their counterparts in denser parts of the universe. These galaxies tend to have lower metallicity, meaning they contain fewer heavy elements like iron and carbon, and they also show slower rates of star formation. But why is this the case, and what does it tell us about how galaxies evolve in such sparse environments? To understand this anomaly, we need to consider the unique conditions within cosmic voids. Unlike galaxies in the crowded filaments of the cosmic web, void galaxies are isolated with fewer neighbors and less interaction with other cosmic structures. This isolation means they have limited access to the raw materials needed for star formation, such as gas and dust. Over time, this scarcity leads to slower rates of star formation compared to galaxies in denser regions. The lower metallicity of void galaxies is another intriguing aspect. Heavy elements are forged in the hearts of stars and spread throughout the universe when those stars explode as supernova. In denser regions, frequent star formation and supernova explosions enrich the surrounding gas with these elements. But in voids where star formation is slower and less frequent, there's less opportunity for heavy elements to accumulate. As a result, void galaxies tend to be metal-poor, offering a glimpse into what galaxies might have looked like in the early universe before heavy elements became abundant. This anomaly isn't just a curiosity, it has significant implications for our understanding of galaxy evolution. Void galaxies act as cosmic time capsules, preserving conditions that are more similar to those of the early universe. By studying them, scientists can gain insights into how galaxies form and evolve in environments with minimal external influences. These galaxies also challenge our assumptions about the role of environment in shaping galactic properties, suggesting that isolation can lead to unique evolutionary pathways. One theory proposes that void galaxies might evolve more slowly than their counterparts in denser regions. Without the gravitational interactions and mergers that are common in crowded cosmic neighborhoods, void galaxies may remain relatively unchanged for billions of years. This slower evolution could explain their lower metallicity and reduced star formation rates, as they simply haven't had the same opportunities to grow and change. The void galaxy anomaly also raises questions about the broader role of cosmic voids in the universe. If void galaxies are so different, what does that mean for the overall structure and evolution of the cosmos? Could these isolated galaxies hold clues about the distribution of dark matter or the influence of dark energy? As we continue to study these enigmatic regions, we may uncover answers that reshape our understanding of the universe's history and future. As we move forward, we'll explore another fascinating aspect of cosmic voids, their potential connection to dark matter. How do these vast, empty regions interact with the invisible substance that makes up most of the universe's mass? Stay with us as we delve into this intriguing mystery. Now, shifting our focus to another layer of mystery, let's explore the role cosmic voids might play in our understanding of dark matter. Dark matter, the invisible substance that makes up most of the universe's mass, has long puzzled scientists. While it doesn't emit light or interact with electromagnetic forces, its gravitational effects are undeniable, shaping the large-scale structure of the cosmos. But what happens to dark matter in the vast, empty regions of cosmic voids? Could these voids hold the key to unlocking some of dark matter's deepest secrets? One intriguing theory suggests that cosmic voids might contain less dark matter than the denser regions of the universe. Since dark matter is thought to clump together, forming the scaffolding for galaxies and galaxy clusters, it makes sense that voids being so empty might have less of it. This idea aligns with observations showing that galaxies in voids move differently than those in denser regions, as if they're being influenced by weaker gravitational forces. If true, studying these voids could help us map the distribution of dark matter more accurately, offering clues about its nature and behavior, but the story doesn't end there. Some scientists propose an even more radical idea, that cosmic voids could be regions where dark matter behaves in unexpected ways, or even where it's entirely absent. This could mean that voids are not just empty of visible matter, but also of the invisible dark matter that dominates the universe. If so, these regions might serve as natural laboratories for testing theories about dark matter's properties and interactions. By comparing the behavior of galaxies in voids to those in denser regions, researchers could uncover subtle differences that reveal more about this elusive substance. Another fascinating possibility is that cosmic voids might act as portals to other dimensions. While this idea ventures into the realm of speculative physics, it's grounded in theories that suggest dark matter could be connected to higher dimensions or alternate realities. If voids are regions where dark matter is sparse or behaves differently, they might also be places where the fabric of space-time is thinner or more malleable, potentially allowing for interactions with other dimensions. While this remains a highly speculative idea, it highlights how cosmic voids could push the boundaries of our understanding of the universe. The study of dark matter in cosmic voids also raises questions about the interplay between dark matter and dark energy, the mysterious force driving the accelerated expansion of the universe. If voids are regions with less dark matter, does that mean dark energy has a stronger influence there? Could the emptiness of voids be a result of dark energy pushing matter apart more effectively in these regions? These are just some of the questions scientists are exploring as they seek to unravel the complex relationship between dark matter, dark energy, and the structure of the universe. As we continue to probe the mysteries of cosmic voids, their connection to dark matter remains a tantalizing area of research. Whether they're regions with less dark matter, testing grounds for new physics, or even gateways to other dimensions, voids offer a unique perspective on one of the universe's greatest enigmas. Next, we'll dive into how cosmic voids might influence the expansion of the universe itself, shedding light on the role of dark energy in shaping the cosmos. Stay tuned as we uncover more about these fascinating cosmic phenomena. Now, let's turn our attention to one of the most profound questions in cosmology: how cosmic voids might be shaping the expansion of the universe itself. As we've seen, these vast, empty regions are more than just gaps in the cosmic web. They could hold the key to understanding the forces driving the universe's accelerated growth. At the heart of this mystery lies dark energy, the enigmatic force that makes up about 68% of the universe's energy content and is responsible for pushing galaxies apart at an ever-increasing rate. But how do cosmic voids fit into this picture? One compelling idea is that voids might act as natural amplifiers for dark energy's effects. In denser regions of the universe, where galaxies and galaxy clusters are packed tightly together, the gravitational pull of matter can counteract dark energy's repulsive force to some extent. But in voids where matter is sparse, there's less gravity to resist dark energy's push. This means that voids could be regions where dark energy's influence is strongest, causing space itself to stretch faster than in other parts of the universe. If this is true, studying the expansion rates within voids could provide critical insights into the nature of dark energy and how it behaves on the largest scales. But the story doesn't stop there. Some scientists suggest that cosmic voids might also serve as testing grounds for new physics beyond our current understanding. For instance, if dark energy's strength varies across different regions of the universe, voids could be the ideal places to detect these variations. By measuring how quickly voids expand compared to denser regions, researchers might uncover subtle differences that challenge our current models of cosmology. This could lead to groundbreaking discoveries, such as evidence that dark energy isn't a constant force but one that changes over time or space. Another intriguing possibility is that voids could reveal clues about the interplay between dark energy and gravity. While gravity pulls matter together, dark energy pushes it apart, and the balance between these two forces shapes the universe's structure. In voids where gravity's influence is weaker, dark energy's effects might dominate, creating a unique environment to study this cosmic tug-of-war. By observing how galaxies move within and around voids, scientists could gain a better understanding of how these forces interact, potentially uncovering new laws of physics that govern the universe's expansion. What's more, the study of voids could also shed light on the ultimate fate of the universe. If dark energy continues to drive accelerated expansion, will voids grow even larger, stretching the fabric of spacetime to its limits? Or could there be a point where dark energy's effects diminish, leading to a different cosmic outcome? These are questions that remain unanswered, but cosmic voids offer a unique window into exploring them. By studying these enigmatic regions, we might not only learn more about dark energy, but also gain insights into the long-term destiny of the cosmos. As we continue to unravel the mysteries of cosmic voids, their role in the universe's expansion stands out as one of the most fascinating areas of research. Whether they're amplifying dark energy's effects, revealing new physics, or offering clues about the universe's future, voids are proving to be far more than empty spaces. They're dynamic regions that could reshape our understanding of the cosmos. Next, we'll explore another intriguing aspect of voids: the mysterious magnetic fields that have been detected within them, and what they might tell us about the universe's hidden forces. Stay with us as we dive deeper into the cosmic unknown. Now, shifting our focus to another layer of cosmic mystery, let's delve into the enigmatic magnetic fields that have been detected within some of these vast voids. While cosmic voids are often thought of as empty, desolate regions, they are far from featureless. In fact, some voids have been found to harbor faint but detectable magnetic fields, adding yet another layer of intrigue to these already puzzling spaces. But where do these magnetic fields come from, and what role do they play in the grand tapestry of the universe? One leading theory suggests that these magnetic fields might be remnants of the early universe, dating back to a time when the cosmos was a seething cauldron of energy and particles. During this chaotic period, turbulent motions of charged particles could have generated magnetic fields that were stretched and amplified as the universe expanded. Over billions of years, these fields might have been preserved in the voids, acting as cosmic fossils that offer a glimpse into the universe's infancy. If this is true, studying these magnetic fields could provide invaluable clues about the conditions that prevailed during the universe's earliest moments. But the origins of these magnetic fields aren't the only mystery. Scientists are also curious about how they might influence the formation and evolution of galaxies and other cosmic structures. Magnetic fields, even weak ones, can affect the motion of charged particles, potentially shaping the way gas and dust accumulate to form stars and galaxies. In voids where matter is sparse, these magnetic fields might play a subtle but significant role in guiding the flow of gas, influencing where and how galaxies form. This could mean that voids aren't just passive regions but active participants in the cosmic dance of structure formation. Another fascinating possibility is that these magnetic fields could be linked to the larger-scale magnetic fields that permeate the universe. Some researchers speculate that the magnetic fields in voids might be connected to those found in galaxy clusters and filaments, forming a vast, interconnected network that spans the cosmic web. If this is the case, understanding the magnetic fields in voids could help us piece together a more complete picture of how magnetism operates on the largest scales, shedding light on its role in shaping the universe's structure. What's more, these magnetic fields might also hold clues about the nature of dark matter and dark energy. While we can't directly observe dark matter, its gravitational effects are felt throughout the cosmos. If magnetic fields in voids interact with dark matter in some way, they could provide indirect evidence of its properties. Similarly, if dark energy influences the behavior of these magnetic fields, studying them could offer new insights into this mysterious force driving the universe's expansion. As we continue to explore the magnetic fields within cosmic voids, one thing is clear: these seemingly empty regions are anything but. They are dynamic, complex environments that challenge our understanding of the universe and its hidden forces. By unraveling the secrets of these magnetic fields, we might uncover new layers of cosmic history and gain a deeper appreciation for the intricate web of forces that shape our universe. Next, we'll turn our attention to another puzzling phenomenon: the unusual cosmic rays detected within voids and what they might reveal about the universe's most energetic processes. Stay with us as we journey further into the cosmic unknown. Now, let's venture into another fascinating mystery lurking within the cosmic voids: the unusual cosmic rays that have been detected in these vast, empty regions. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. And while they are found throughout the universe, their presence in voids is particularly puzzling. Why would these sparse, seemingly empty regions be home to such energetic phenomena? The answer might lie in some of the most extreme and exotic processes in the cosmos. One possible source of these cosmic rays is supermassive black holes. These colossal objects, often found at the centers of galaxies, are known to produce immense amounts of energy. When matter falls into a black hole, it can be accelerated to incredible speeds, creating jets of particles that shoot out into space. These jets can extend far beyond their host galaxies, potentially reaching into the void. If a supermassive black hole's jet happens to point toward a void, it could flood that region with high-energy cosmic rays, even though the void itself contains little to no matter. This would make voids a kind of cosmic highway for these energetic particles, carrying them across vast distances. But supermassive black holes aren't the only suspects. Another intriguing possibility is that these cosmic rays come from exotic particles or processes that we have yet to fully understand. For instance, some theories suggest that dark matter, the mysterious substance that makes up most of the universe's mass, could decay or annihilate, releasing high-energy particles in the process. If this happens within voids, it could explain the presence of cosmic rays in these otherwise empty regions. Alternatively, cosmic rays might be produced by rare, high-energy events like the collision of neutron stars or the explosion of massive stars, whose remnants could drift into voids over time. What makes these cosmic rays even more fascinating is their potential to reveal secrets about the universe's most extreme environments. By studying the energy and composition of cosmic rays in voids, scientists can learn about the processes that created them, even if those processes occurred billions of years ago. This makes cosmic rays a kind of cosmic messenger, carrying information from some of the most distant and energetic events in the universe. Moreover, the detection of cosmic rays in voids challenges our understanding of how these particles travel through space. Cosmic rays are typically thought to be deflected by magnetic fields, which are stronger in regions with more matter, like galaxies and galaxy clusters. But in voids where magnetic fields are weaker, cosmic rays might travel more freely, allowing them to reach us from greater distances. This could make voids a unique window into the universe's most energetic phenomena, offering insights that are harder to obtain in denser regions of space. As we continue to explore the mysteries of cosmic rays in voids, one thing is certain: these high-energy particles are more than just a curiosity. They are a key to understanding the universe's most extreme processes and the forces that shape it on the largest scales. Next, we'll turn our attention to another enigmatic aspect of cosmic voids, their potential role in the reionization of the universe and how they might hold clues to one of the most transformative periods in cosmic history. Stay with us as we uncover more secrets of the cosmic web's voids. Now, let's shift our focus to one of the most transformative periods in the history of the universe, the era of reionization. This pivotal phase, which occurred hundreds of millions of years after the Big Bang, marked the moment when the first stars and galaxies began to illuminate the cosmos, ionizing the surrounding hydrogen gas and fundamentally changing the universe's structure. But what role did cosmic voids play in this dramatic process? Surprisingly, these vast, empty regions might have been more influential than we once thought. During the early universe, the cosmos was filled with a dense fog of neutral hydrogen gas. As the first stars and galaxies formed, their intense ultraviolet light began to ionize this gas, stripping electrons from hydrogen atoms and turning the universe from opaque to transparent. This process, known as reionization, didn't happen uniformly. Instead, it occurred in patches, with some regions ionizing faster than others. Cosmic voids, with their sparse distribution of matter, likely played a unique role in this uneven progression. One theory suggests that voids acted as natural conduits for the ionizing radiation produced by early galaxies. Because voids contain less matter, the ultraviolet light from these galaxies could travel farther and more freely through these regions, helping to ionize distant pockets of hydrogen gas. In this way, voids might have served as cosmic highways, allowing the light from the first stars and galaxies to spread more efficiently across the universe. Without these vast, empty regions, reionization might have taken much longer, delaying the universe's transition to transparency. However, studying the role of voids in reionization is no easy task. This era occurred over 13 billion years ago, and the light from that time has been stretched and dimmed by the expansion of the universe, making it incredibly faint and difficult to detect. Additionally, the sparse nature of voids means there are fewer clues left behind for scientists to analyze. To overcome these challenges, researchers rely on sophisticated simulations and observations of distant quasars, whose light passes through ancient voids, leaving behind telltale signatures in the form of absorption lines. These lines provide a glimpse into the conditions of the early universe, helping us piece together how reionization unfolded. Another intriguing possibility is that voids might have influenced the formation of the first galaxies themselves. The lower density of matter in voids could have allowed galaxies to form more slowly, creating a unique population of early galaxies with distinct properties. These galaxies, in turn, might have contributed to reionization in ways that are still not fully understood. By studying the interplay between voids and early galaxies, scientists hope to uncover new insights into how the universe transitioned from darkness to light. As we continue to explore the mysteries of reionization, cosmic voids remain a key piece of the puzzle. Their role in shaping the early universe highlights just how interconnected the cosmos truly is, with even the emptiest regions playing a vital part in its evolution. Next, we'll delve into another speculative yet fascinating idea: the connection between cosmic voids and the quantum foam, the fabric of space-time at the smallest scales. Stay with us as we uncover more secrets of the cosmic web's voids. Now, let's venture into one of the most mind-bending ideas in modern cosmology: the potential connection between cosmic voids and quantum foam. At the smallest scales imaginable, space-time itself is thought to be a seething, frothy sea of fluctuations known as quantum foam. This concept, rooted in quantum mechanics and general relativity, suggests that the fabric of reality is not smooth and continuous but rather a turbulent, ever-changing landscape at the tiniest levels. But how could this microscopic chaos relate to the vast, empty expanses of cosmic voids? The answer lies in the intriguing possibility that these voids might be windows into the quantum nature of spacetime itself. Quantum foam is a theoretical framework that attempts to describe the behavior of spacetime at scales so small that the rules of classical physics break down. At these scales, particles and energy fluctuate wildly, creating a chaotic, bubbling foam of spacetime. While this phenomenon is impossible to observe directly due to its minuscule size, its effects could ripple outward, influencing larger structures in the universe. Cosmic voids, with their sparse matter and immense scales, might be the perfect places to look for clues about this quantum underpinning of reality. Some scientists speculate that the emptiness of voids could amplify or preserve subtle quantum effects, making them detectable on a cosmic scale. One of the most exciting implications of this connection is its potential to shed light on quantum gravity, the long-sought theory that would unify quantum mechanics and general relativity. Currently, these two pillars of modern physics describe the universe in fundamentally different ways, and reconciling them remains one of the greatest challenges in science. If cosmic voids indeed hold traces of quantum foam, they could provide a unique testing ground for theories of quantum gravity. For instance, the way spacetime behaves in the vast emptiness of a void might reveal subtle deviations from the predictions of classical physics, offering hints about the quantum nature of gravity. Another fascinating idea is that cosmic voids could act as natural laboratories for studying the interplay between quantum fluctuations and large-scale cosmic structures. In the dense regions of the universe, the effects of quantum foam might be drowned out by the overwhelming presence of matter and energy. But in the near-perfect vacuum of a void, these tiny fluctuations could accumulate over vast distances, potentially influencing the formation and evolution of galaxies and other structures. This could mean that voids are not just empty spaces but dynamic regions where the quantum and cosmic scales intersect in profound ways. Of course, these ideas remain highly speculative, and much work is needed to test them. Observing the effects of quantum foam in cosmic voids would require incredibly precise measurements and advanced technology, pushing the boundaries of what we can currently achieve. However, the mere possibility that voids could hold the key to understanding quantum gravity is enough to inspire scientists to keep exploring. As we continue to probe the mysteries of the universe, cosmic voids may yet reveal secrets that reshape our understanding of reality itself. With this speculative yet captivating connection between voids and quantum foam in mind, let's turn our attention to another intriguing phenomenon: the role of cosmic voids in galaxy formation. How do these vast, empty regions influence the birth and evolution of galaxies? Stay with us as we uncover more layers of the cosmic web's mysteries. Now, let's shift our focus to a fascinating aspect of cosmic voids: their potential role in the formation of galaxies. While voids are often thought of as empty, lifeless regions, they might actually play a crucial part in shaping the universe's structure. In fact, some scientists believe that these vast, sparse areas could act as cosmic nurseries, fostering the birth and evolution of unique types of galaxies that are rarely found in denser regions of the universe. In the dense, crowded regions of the cosmic web, galaxies often collide and interact, leading to rapid star formation and the creation of massive, bright galaxies. But in the quiet emptiness of cosmic voids, the story is quite different. Here, galaxies evolve in relative isolation, free from the gravitational tug of war that dominates more crowded areas. This isolation allows for slower, more gradual processes, which can result in the formation of galaxies with unusual properties. For example, void galaxies often have lower metallicity, meaning they contain fewer heavy elements compared to galaxies in denser regions. This lack of heavy elements can lead to slower star formation rates and the creation of smaller, dimmer galaxies. But why does this matter? These void galaxies, though rare, offer a unique window into the early universe. Their simpler chemical makeup and slower evolution resemble the conditions of the universe shortly after the Big Bang. By studying these galaxies, scientists can gain insights into how the first galaxies formed and evolved over billions of years. In a sense, cosmic voids act as cosmic time capsules, preserving a snapshot of the universe's infancy. Another intriguing idea is that voids might serve as testing grounds for theories of galaxy formation. In denser regions, the complex interplay of gravity, dark matter, and other forces can make it difficult to isolate specific factors that influence galaxy evolution. But in voids where these forces are less pronounced, scientists can study the fundamental processes that drive galaxy formation in a more controlled environment. This could help refine our understanding of how galaxies grow and change over time. Of course, the role of voids in galaxy formation is still a topic of active research. While some theories suggest that voids could be cosmic nurseries for rare galaxies, others propose that these regions might simply be too empty to support significant galaxy formation. The truth likely lies somewhere in between, with voids playing a nuanced role in the grand tapestry of the universe. As we continue to explore the mysteries of cosmic voids, one thing is clear: these seemingly empty regions are far from lifeless. They may hold the key to understanding not only how galaxies form, but also how the universe itself has evolved over billions of years. With that in mind, let's turn our attention to another captivating phenomenon: the role of cosmic voids in shaping the large-scale structure of the universe. How do these vast, empty regions influence the cosmic web as a whole? Stay with us as we dive deeper into the mysteries of the cosmos. Now, let's take a closer look at how cosmic voids might have played a pivotal role in shaping the very fabric of the universe. These vast, seemingly empty regions are not just passive spaces, they are active participants in the grand story of cosmic evolution. By influencing the distribution of matter and the formation of the cosmic web, voids have helped sculpt the universe into the intricate structure we observe today. The cosmic web, often described as the universe's skeleton, is a vast network of filaments made up of galaxies, gas, and dark matter. These filaments stretch across the cosmos, connecting clusters of galaxies and enclosing enormous voids. But how do these voids fit into the picture? Think of them as the negative spaces in a cosmic painting. While the filaments are dense and bustling with activity, the voids are the quiet, expansive areas that give the web its shape and balance. Without voids, the cosmic web would lose its defining structure, collapsing into a chaotic mess. One of the most fascinating aspects of cosmic voids is their role in the distribution of matter. During the early universe, tiny fluctuations in density led to the formation of both dense regions and empty ones. As the universe expanded, these fluctuations grew, with matter clumping together to form galaxies and clusters, while the less dense regions evolved into voids. Over billions of years, gravity pulled matter into the filaments, leaving the voids increasingly empty. This process not only shaped the cosmic web, but also influenced the movement of galaxies and the flow of cosmic energy. But voids are more than just empty spaces. They act as cosmic pressure points, influencing the behavior of the surrounding matter. For instance, the gravitational pull of the dense filaments can draw matter away from the voids, creating a kind of cosmic tug of war. This interplay between voids and filaments has helped regulate the growth of the cosmic web, ensuring that it maintains its delicate balance. Moreover, voids might hold clues about the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids are less dense, they are more sensitive to the effects of dark energy. By studying how voids expand and evolve, scientists can gain insights into the properties of dark energy and its impact on the universe's fate. In this way, voids are not just passive observers of cosmic evolution. They are active participants, shaping and being shaped by the forces that govern the cosmos. As we continue to explore the mysteries of cosmic voids, one thing becomes clear: These seemingly empty regions are far from insignificant. They are integral to the universe's structure, playing a crucial role in the distribution of matter, the formation of the cosmic web, and the evolution of the cosmos itself. With that in mind, let's turn our attention to another intriguing phenomenon: the possibility that time itself flows differently within these vast, empty regions. Could cosmic voids hold the key to understanding the nature of space-time? Stay with us as we delve deeper into the mysteries of the universe. Now, let's shift our focus to a mind-bending concept that challenges our understanding of time itself. Could it be that time flows differently within the vast emptiness of cosmic voids? This intriguing possibility opens up a whole new dimension to our exploration of these enigmatic regions. According to Einstein's theory of relativity, time is not a fixed universal constant. Instead, it is influenced by gravity and the curvature of spacetime. In regions of intense gravitational pull, such as near black holes or massive galaxy clusters, time slows down, a phenomenon known as time dilation. But what about the opposite scenario? In the sparse, low-density environments of cosmic voids, where gravity's influence is significantly weaker, could time actually speed up? This idea isn't just speculative, it has a basis in scientific theory. In the absence of strong gravitational fields, space-time behaves differently. Some researchers suggest that the expansion of the universe, driven by dark energy, might cause time to flow faster in voids compared to denser regions. If true, this would mean that clocks in voids would tick slightly faster than those in galaxy clusters or along the filaments of the cosmic web. The implications of this are profound. If time dilation occurs in voids, it could reshape our understanding of space-time and the fundamental laws of physics. For instance, it might provide new insights into the nature of dark energy and how it interacts with the fabric of the universe. It could also challenge our current models of cosmic evolution, forcing us to reconsider how we measure time and distance on a universal scale. But how do we test such a radical idea? One approach involves studying the light from distant galaxies that pass through voids. If time flows faster in these regions, the light might exhibit subtle changes in frequency or wavelength, providing clues about the behavior of spacetime. Another possibility is to observe the motion of galaxies within and around voids, looking for anomalies that could hint at variations in the flow of time. While the concept of time dilation in voids is still largely theoretical, it highlights just how much we have yet to learn about these mysterious regions. They are not just empty spaces, they are laboratories for testing the limits of our understanding of the universe. As we continue to explore the cosmos, cosmic voids may hold the key to unlocking some of the deepest mysteries of spacetime and relativity. With this fascinating possibility in mind, let's turn our attention to another cosmic puzzle: the role of voids in the propagation of gravitational waves. Could these vast, empty regions influence how ripples in spacetime travel across the universe? Stay with us as we dive deeper into the mysteries of the cosmos. Now, let's venture into another fascinating aspect of cosmic voids: their potential influence on gravitational waves. These ripples in space-time, first predicted by Einstein over a century ago, have opened a new window into the universe, allowing us to observe events like black hole mergers and neutron star collisions. But how do cosmic voids, with their vast emptiness, fit into this picture? Could they alter the way gravitational waves travel through the cosmos? Gravitational waves are incredibly sensitive to the fabric of space-time. As they propagate through the universe, they can be affected by the density and structure of the regions they pass through. In dense areas like galaxy clusters, the intense gravitational fields can subtly distort these waves, much like how light bends when passing through a lens. But in cosmic voids, where matter is sparse and gravity's grip is weak, the behavior of gravitational waves might be quite different. One intriguing possibility is that voids could act as cosmic lenses for gravitational waves, but in a way that's opposite to what we see with light. Instead of bending or focusing the waves, the low-density environment of a void might allow them to travel more freely with less distortion. This could provide a clearer signal, making it easier for scientists to study the properties of the waves and the events that produce them. In essence, voids might serve as natural laboratories for observing gravitational waves in their purest form. But the implications go even further. If gravitational waves behave differently in voids, it could offer new insights into the nature of gravity itself. For example, it might help us test alternative theories of gravity that deviate from Einstein's general relativity. Some of these theories predict that gravity could behave differently in low-density environments, and voids provide the perfect testing ground for such ideas. By analyzing how gravitational waves propagate through these regions, we could uncover clues about whether our current understanding of gravity holds true across the entire universe. Moreover, studying gravitational waves in voids could shed light on the distribution of dark matter. While dark matter doesn't interact with light, it does exert gravitational influence. If voids contain less dark matter than denser regions, this could affect how gravitational waves travel through them. By comparing wave signals from different parts of the universe, scientists might be able to map the distribution of dark matter with unprecedented precision. Of course, this is still a developing field of research. Detecting and analyzing gravitational waves is already a monumental challenge, and studying their behavior in voids adds another layer of complexity. But as our technology and methods improve, cosmic voids could become invaluable tools for probing the deepest mysteries of gravity and space-time. With this in mind, let's turn our attention to another cosmic enigma: the role of voids in the inflationary period of the universe. Could these vast, empty regions hold clues about the rapid expansion that shaped the cosmos as we know it? Stay with us as we continue to unravel the secrets of the cosmic web. Now, shifting our gaze to the very beginnings of the universe, let's explore how cosmic voids might hold the key to understanding one of the most pivotal moments in cosmic history, the inflationary period. This era, occurring just fractions of a second after the Big Bang, saw the universe expand at an unimaginable rate, stretching far beyond the speed of light. But how do the vast, empty regions of cosmic voids connect to this explosive chapter? Could they preserve echoes of that rapid expansion, offering us a glimpse into the universe's infancy? Cosmic inflation is a cornerstone of modern cosmology, explaining why the universe appears so uniform on large scales and why tiny quantum fluctuations grew into the galaxies and voids we see today. However, testing inflation theories is no small feat. The evidence lies in the faint imprints left on the cosmic microwave background radiation, the afterglow of the Big Bang. But here's where cosmic voids come into play. These regions, with their sparse matter and unique gravitational properties, might act as time capsules, preserving subtle clues about the inflationary epoch. One intriguing idea is that voids could have formed as a direct result of inflation. During this rapid expansion, quantum fluctuations were stretched to cosmic scales, creating regions of slightly higher and lower density. Over billions of years, these underdense regions evolved into the voids we observe today. If this is true, studying the size, distribution, and properties of voids could help us refine our understanding of inflation. For instance, the way voids are arranged in the cosmic web might reflect the specific conditions of the inflationary period, offering a new way to test competing theories. But the challenges are significant. Inflation occurred at energy scales far beyond what we can recreate in laboratories, and the signals it left behind are incredibly faint. Cosmic voids, while vast, are also subtle in their influence. Detecting their connection to inflation requires precise measurements of the cosmic microwave background and the large-scale structure of the universe. Even then, distinguishing between the effects of inflation and other cosmic processes is a daunting task. Another hurdle is the sheer complexity of the data. The universe is a messy place filled with overlapping signals from galaxies, dark matter, and other cosmic phenomena. Isolating the specific imprint of inflation within voids requires advanced simulations and cutting-edge observational techniques. Yet, despite these challenges, the potential rewards are immense. If we can uncover the link between voids and inflation, it could revolutionize our understanding of the universe's origins. As we continue to probe these enigmatic regions, we're reminded that the universe is full of surprises. Cosmic voids, once thought to be mere empty spaces, might hold the answers to some of the most profound questions in cosmology. And with that, let's turn our attention to another speculative yet captivating idea. Could cosmic voids be evidence of a multiverse? Stay with us as we explore this mind-bending possibility. Now, let's venture into one of the most speculative yet fascinating ideas in cosmology. Could cosmic voids be evidence of a multiverse? This concept pushes the boundaries of our understanding, suggesting that the vast, empty regions we observe might not just be gaps in our universe, but could instead be the boundaries or intersections between multiple universes. Imagine cosmic voids as the bubbles separating different cosmic realms, each with its own unique laws of physics and history. The multiverse theory proposes that our universe is just one of countless others, each existing in its own distinct space. If this is true, then the voids we see might be the regions where these universes barely touch or overlap. These areas, with their extreme emptiness and unique gravitational properties, could act as the walls between universes, offering a tantalizing glimpse into a reality far beyond our own. But how could we ever detect such a thing? The answer lies in the subtle clues these voids might leave behind. One possibility is that the distribution and structure of cosmic voids could reveal patterns that are inconsistent with a single universe model. For example, if voids are arranged in a way that suggests they were shaped by interactions with other universes, this could be a smoking gun for the multiverse. Additionally, the behavior of matter and energy within voids might show anomalies that can't be explained by our current understanding of physics. These irregularities could hint at the influence of neighboring universes where the laws of nature might be entirely different. Another intriguing angle is the idea that cosmic voids could be regions where the fabric of space-time is stretched thin, creating windows into other universes. If this is the case, then studying the properties of voids such as their density, temperature, and gravitational effects might provide indirect evidence of a multiverse. For instance, certain voids might exhibit unusual gravitational lensing effects or emit faint signals that don't align with our expectations for a single, isolated universe. Of course, these ideas remain highly speculative, and the challenges of testing them are immense. The multiverse theory, by its very nature, exists at the edge of what we can observe and measure. Yet, cosmic voids offer a unique opportunity to explore these ideas in a way that's grounded in observable phenomena. By studying these enigmatic regions, we might one day uncover clues that point to the existence of other universes, forever changing our understanding of reality. As we ponder the possibility of a multiverse, it's worth remembering that the universe is full of mysteries waiting to be unraveled. Cosmic voids, once thought to be mere empty spaces, might hold the key to unlocking one of the greatest questions of all: are we alone in the cosmos, or is our universe just one of many? With that thought, let's turn our attention to another fascinating aspect of cosmic voids: their role in preserving the history of the early universe. Stay tuned as we explore how these regions might act as cosmic time capsules, offering us a glimpse into the distant past. Shifting our focus to the past, let's explore how cosmic voids might serve as cosmic archaeologists, preserving secrets from the early universe. These vast, empty regions could hold clues about the conditions and events that shaped the cosmos billions of years ago, offering us a unique window into the universe's infancy. One of the most intriguing possibilities is that voids might act as time capsules, capturing the faint echoes of the universe's formative moments. During the early stages of cosmic evolution, the universe was a dense, hot soup of particles and energy. As the cosmos expanded, matter clumped together to form galaxies and galaxy clusters, while the regions between them became increasingly empty, creating the voids we see today. Because these voids have remained relatively undisturbed over billions of years, they might still carry imprints of the universe's initial conditions. For example, the distribution of matter within and around voids could reveal details about the early universe's density fluctuations. These fluctuations, which eventually led to the formation of galaxies and large-scale structures, are thought to have originated during the inflationary period, a rapid expansion that occurred just moments after the Big Bang. By studying the patterns of matter in and around voids, scientists might be able to reconstruct the conditions of this critical era, shedding light on how the universe transitioned from a smooth, uniform state to the complex web of structures we observe today. Another fascinating aspect is the role of voids in preserving ancient light. The cosmic microwave background radiation, or CMB, is the oldest light in the universe, dating back to just 380,000 years after the Big Bang. While this light has been studied extensively, voids could offer a new perspective. Because voids contain so little matter, light passing through them is less likely to be scattered or absorbed, potentially allowing us to observe the CMB in its purest form. This could provide unprecedented insights into the early universe's temperature, density, and composition. Additionally, voids might help us understand the reionization epoch, a period when the first stars and galaxies formed and ionized the surrounding hydrogen gas. This process, which occurred hundreds of millions of years after the Big Bang, is still poorly understood. Voids, with their low density and minimal interference, could preserve traces of this era, offering clues about how the first structures in the universe influenced their surroundings. Of course, studying cosmic archaeology through voids is no easy task. The faint signals and subtle patterns we're looking for are incredibly difficult to detect, requiring advanced telescopes and innovative techniques. Yet, the potential rewards are immense. By unlocking the secrets hidden within these empty regions, we could gain a deeper understanding of the universe's origins and evolution, piecing together the story of how everything we see today came to be. As we continue to explore the mysteries of cosmic voids, it's clear that these seemingly empty spaces are anything but. They are treasure troves of information, holding the keys to understanding the universe's past, present, and perhaps even its future. With that in mind, let's turn our attention to another captivating aspect of voids: their potential role in the search for exoplanets. Stay tuned as we delve into how these enigmatic regions might influence the hunt for worlds beyond our solar system. Now, let's venture into a fascinating intersection of cosmic voids and the search for exoplanets. While voids are often thought of as empty, barren regions, they might play a surprising role in our quest to discover planets beyond our solar system. The unique conditions within these vast, low-density areas present both challenges and opportunities for astronomers hunting for distant worlds. One of the biggest hurdles in detecting exoplanets within voids is the sheer lack of material. Most exoplanet discoveries rely on methods like the transit technique, where a planet passes in front of its host star, causing a slight dip in the star's brightness. However, in voids, stars are few and far between, making it much harder to find suitable candidates for observation. The sparse distribution of stars means fewer opportunities to detect these subtle changes in light, requiring astronomers to cast a much wider net in their searches. Another challenge lies in the nature of the stars that do exist within voids. These stars are often older and less active than those in denser regions of the universe, which can make it harder to spot the telltale signs of orbiting planets. For example, younger stars tend to have more pronounced stellar activity, such as flares and sunspots, which can obscure the faint signals of exoplanets. In contrast, the quieter, older stars in voids might not provide as many detectable clues, even if planets are present. Despite these challenges, voids could still hold valuable insights for exoplanet research. One intriguing possibility is that the unique environment of voids might influence the types of planets that form there. In denser regions of the universe, the gravitational interactions between stars and other celestial bodies can disrupt planetary systems, potentially ejecting planets into space or altering their orbits. In voids where such interactions are rare, planetary systems might remain more stable over time, offering a clearer picture of how planets form and evolve in isolation. Additionally, the lack of interference in voids could make them ideal laboratories for studying exoplanet atmospheres. When light from a star passes through a planet's atmosphere, it carries information about the gases present, which can be analyzed to determine the planet's composition. In voids where there's less cosmic dust and gas to scatter or absorb this light, the signals from exoplanet atmospheres might be cleaner and easier to interpret. This could provide astronomers with unprecedented details about the conditions on these distant worlds, including the potential for habitability. Of course, unlocking these secrets will require cutting-edge technology and innovative approaches. Future telescopes, like the James Webb Space Telescope and its successors, will play a crucial role in overcoming the challenges posed by voids. By combining advanced imaging techniques with targeted observations of void regions, astronomers might uncover a wealth of new exoplanets, each offering a unique glimpse into the diversity of planetary systems across the cosmos. As we continue to explore the mysteries of cosmic voids, their connection to exoplanet discovery reminds us that even the emptiest regions of space can hold profound significance. These vast, seemingly desolate areas might just be the key to unlocking new worlds and expanding our understanding of the universe. With that in mind, let's turn our attention to another captivating mystery: how cosmic voids might influence the distribution of cosmic radiation and what that means for life in the universe. Now, let's shift our focus to another intriguing aspect of cosmic voids: their potential role in shaping the distribution of cosmic radiation. Cosmic radiation, composed of high-energy particles like protons and atomic nuclei, permeates the universe, influencing everything from the formation of stars to the conditions necessary for life. But how do the vast, empty regions of cosmic voids interact with this invisible yet powerful force? One of the most fascinating possibilities is that voids might act as natural shields, reducing the intensity of cosmic radiation within their boundaries. In denser regions of the universe, cosmic rays are constantly scattered and accelerated by magnetic fields and interactions with matter. However, in voids where matter is sparse and magnetic fields are weaker, cosmic rays might travel more freely, losing energy over greater distances. This could create pockets of lower radiation levels, potentially offering safer environments for life to emerge and thrive. On the other hand, the lack of material in voids might also lead to unexpected consequences. Without the usual scattering effects of matter, cosmic rays could retain their high energy for longer periods, potentially creating regions where radiation levels are more intense. This raises questions about the habitability of planets within or near voids. Could life exist in such environments, or would the radiation prove too harsh? The answer might depend on the specific conditions within each void, as well as the protective mechanisms of any potential life forms. Another intriguing angle is how voids might influence the propagation of cosmic radiation across the universe. As cosmic rays travel through voids, their paths could be altered by the subtle gravitational effects of dark matter or the weak magnetic fields present in these regions. This could lead to variations in how radiation is distributed, creating patterns that astronomers could study to better understand the large-scale structure of the universe. By mapping these patterns, scientists might gain new insights into the nature of dark matter, the behavior of cosmic rays, and even the history of the cosmos itself. The implications for life are equally compelling. If voids do indeed reduce radiation levels, they could serve as cosmic oases, offering more stable environments for the development of complex organisms. Conversely, if radiation levels are higher, life in these regions might need to evolve unique adaptations to survive. Either way, the study of cosmic radiation in voids could provide valuable clues about where and how life might exist beyond Earth. As we continue to explore the mysteries of cosmic voids, their relationship with cosmic radiation opens up a new frontier in our understanding of the universe. These vast, seemingly empty regions might hold the key to unlocking secrets about the conditions necessary for life, the behavior of high-energy particles, and the intricate balance of forces that shape our cosmos. With that in mind, let's turn our attention to another captivating mystery: how cosmic voids might hold the key to solving other cosmic mysteries, such as the nature of dark energy or the fate of the universe. Now, let's venture into one of the most profound questions in modern cosmology: how cosmic voids might hold the key to unraveling some of the universe's greatest mysteries. These vast, empty regions are not just empty spaces. They could be the missing pieces in our understanding of dark energy, the expansion of the universe, and even its ultimate fate. Dark energy, the mysterious force driving the accelerated expansion of the universe, remains one of the biggest puzzles in science. While we know it exists because of its effects on galaxies and cosmic structures, its true nature is still unknown. Cosmic voids, with their unique properties, might offer a unique testing ground for studying dark energy. The way voids expand and evolve over time could provide clues about how dark energy interacts with the fabric of space-time. For instance, if voids are growing faster than expected, it might suggest that dark energy is stronger in these regions, or that its effects vary across the cosmos. But the mysteries don't stop there. Voids might also help us understand the ultimate fate of the universe. Will the universe continue expanding forever, eventually becoming a cold, dark void itself? Or will it collapse back in on itself in a big crunch? The behavior of cosmic voids could hold the answers. By studying how voids grow and interact with surrounding structures, scientists can test different models of cosmic evolution. For example, if voids are found to be expanding at an accelerating rate, it could support the idea of a big freeze, where the universe becomes increasingly sparse and cold over time. Another intriguing possibility is that voids might reveal hidden connections between dark energy and dark matter. While dark matter is thought to clump together, forming the scaffolding for galaxies and galaxy clusters, dark energy seems to work in opposition, pushing everything apart. Voids, with their low concentrations of both matter and dark matter, might be the perfect places to study how these two mysterious forces interact. Could voids be regions where dark energy dominates, overpowering the gravitational pull of dark matter? Or do they represent a delicate balance between the two? Finally, cosmic voids might even shed light on the origins of the universe itself. Some theories suggest that voids could be remnants of the early universe, regions where quantum fluctuations during the Big Bang left behind less matter. If true, studying voids could provide a window into the conditions of the cosmos just moments after its birth. This could help us refine our understanding of cosmic inflation, the rapid expansion that occurred in the universe's first fraction of a second. As we explore these possibilities, it becomes clear that cosmic voids are far from empty. They are dynamic, evolving regions that could hold the answers to some of the most profound questions in science. From the nature of dark energy to the fate of the universe, these enigmatic spaces might just be the key to unlocking the secrets of our cosmos. With that in mind, let's turn our attention to another captivating mystery: how cosmic voids might be hiding alien civilizations, and what that could mean for the search for life beyond Earth. Now, let's shift our gaze to one of the most intriguing possibilities. Could cosmic voids be hiding alien civilizations? While these vast, empty regions seem inhospitable, they might just be the perfect hiding spots for advanced extraterrestrial life. The idea might sound like science fiction, but when we consider the unique properties of voids, it's not as far-fetched as it seems. One of the biggest challenges in the search for alien life is the sheer emptiness of cosmic voids. With so few stars and galaxies, these regions are naturally less likely to host life as we know it. However, this very sparseness could make voids ideal for civilizations that have evolved beyond the need for dense stellar environments. Advanced alien societies might have developed technologies that allow them to thrive in low-density regions, harnessing resources in ways we can't yet imagine. Another factor to consider is the difficulty of detecting life in voids. Our current methods for finding extraterrestrial life rely heavily on observing planets within star systems, looking for signs like atmospheric biosignatures or artificial signals. But in voids where stars are few and far between, these methods become nearly useless. If alien civilizations exist in these regions, they might be intentionally avoiding detection, using the vast emptiness of voids as a shield. Moreover, the unique conditions of voids could foster life forms that are entirely different from anything we've encountered. For example, life in voids might not rely on sunlight or organic chemistry as we know it. Instead, it could be powered by dark energy, dark matter, or other exotic processes that are still beyond our understanding. This raises the tantalizing possibility that voids could be home to life forms that are not just alien in origin, but alien in their very nature. Of course, the challenges of exploring voids are immense. The distances involved are staggering, and the lack of light and matter makes it difficult to gather data. But if we ever do find evidence of life in these regions, it could revolutionize our understanding of biology, technology, and the universe itself. As we ponder the possibility of alien civilizations hidden within cosmic voids, one thing becomes clear: these enigmatic regions are not just empty spaces. They are frontiers of discovery, holding secrets that could change everything we know about life, the universe, and our place within it. With that in mind, let's turn to the final frontier of our exploration: how cosmic voids might shape the future of space exploration, and what mysteries they could reveal in the years to come. As we venture into the final chapter of our cosmic journey, let's turn our attention to the future. What role might cosmic voids play in the next era of space exploration? These vast, mysterious regions, often overlooked in favor of more densely populated areas of the universe, could hold the key to unlocking some of the greatest mysteries of the cosmos. Far from being empty wastelands, voids may represent the next frontier for scientific discovery, offering opportunities to test new technologies, explore uncharted territories, and perhaps even rewrite the rules of physics as we know them. One of the most exciting possibilities is the development of advanced spacecraft capable of traversing the immense distances of cosmic voids. Current missions are limited by the speed of light and the vastness of space, but future technologies, such as warp drives or quantum propulsion systems, could make it possible to explore these regions in ways we can only dream of today. Imagine a mission that sends probes into the heart of a void, equipped with sensors designed to detect dark energy, dark matter, or even signs of exotic life forms. Such a mission could revolutionize our understanding of the universe and open up entirely new fields of study. Another intriguing aspect of void exploration is the potential to study the effects of extreme isolation on cosmic structures. Voids are not completely empty. They contain faint traces of matter, radiation, and perhaps even undiscovered phenomena. By studying these sparse environments, scientists could gain insights into how galaxies form and evolve in the absence of dense stellar populations. This could help us understand the role of voids in shaping the large-scale structure of the universe and provide clues about the nature of cosmic expansion. Moreover, cosmic voids could serve as natural laboratories for testing theories about the fundamental forces of nature. For example, the low-density environment of voids might allow us to observe subtle effects of gravity, dark energy, or even quantum mechanics that are impossible to detect in more crowded regions of space. Future missions could deploy sensitive instruments to measure these effects, potentially leading to breakthroughs in our understanding of physics and the universe itself. But the challenges of exploring voids are not to be underestimated. The distances involved are staggering, and the lack of light and matter makes navigation and data collection incredibly difficult. However, these challenges also present opportunities for innovation. Future missions might rely on autonomous spacecraft, artificial intelligence, and advanced communication systems to overcome the hurdles of void exploration. These technologies could pave the way for a new era of space science, where the boundaries of human knowledge are pushed further than ever before. As we look to the future, one thing is certain: cosmic voids are not just empty spaces to be ignored. They are windows into the unknown, offering a glimpse of the universe's deepest secrets. Whether it's through the discovery of new physics, the detection of alien life, or the development of groundbreaking technologies, the exploration of voids has the potential to transform our understanding of the cosmos and our place within it. And with that, we conclude our journey through the 25 unexplained phenomena of cosmic voids, leaving us with a sense of wonder and anticipation for what lies ahead in the vast, uncharted reaches of space. Now, let's take a closer look at one of the most enigmatic regions of the cosmos, the Boötes Void. Spanning an astonishing 330 million light-years, this colossal void is one of the largest known structures in the universe. But what makes it truly fascinating is not just its size, but the mysteries it holds within its seemingly empty expanse. Could this void hold clues about dark energy, the mysterious force driving the accelerated expansion of the universe? Or might it conceal undiscovered galaxies hidden in the shadows of its vast emptiness? The Boötes Void was first discovered in the 1980s, and its sheer scale immediately captured the attention of astronomers. Unlike most regions of space, which are filled with galaxies, stars, and cosmic structures, this void is eerily sparse. In fact, it contains only a fraction of the galaxies you'd expect to find in a space of its size. This has led scientists to wonder what could have caused such a vast region to remain so empty. One theory suggests that dark energy, the force responsible for pushing the universe apart, might play a role. The low density of matter in the void could amplify the effects of dark energy, creating a unique environment where its influence is more pronounced than in denser regions of space. But the Boötes Void isn't just a playground for dark energy theories. It also raises questions about the formation and distribution of galaxies. Could there be galaxies lurking within the void that we simply haven't detected yet? The faint light from these potential galaxies might be too dim for our current telescopes to pick up, especially against the backdrop of such an empty region. If future missions or more advanced instruments were to uncover these hidden galaxies, it could reshape our understanding of how galaxies form and evolve in the most isolated corners of the universe. Another intriguing possibility is that the Boötes Void might be home to exotic forms of matter or energy that we have yet to discover. The extreme conditions of the void, its near total emptiness and low radiation levels, could create an environment where unusual phenomena occur. For instance, some scientists speculate that the void might contain traces of primordial matter, left over from the early universe, or even evidence of quantum effects that are impossible to observe in more crowded regions of space. Exploring the Boötes Void is no small feat. Its immense size and the challenges of observing such a sparse region make it a daunting target for astronomers. Yet the potential rewards are immense. By studying this void, we could gain new insights into the nature of dark energy, the distribution of matter in the universe, and even the fundamental laws of physics. Future missions equipped with cutting-edge technology might one day venture into this cosmic desert, uncovering secrets that could revolutionize our understanding of the cosmos. As we ponder the mysteries of the Boötes Void, one thing becomes clear. This vast, empty region is far from being a cosmic dead end. It's a frontier of discovery, offering a unique window into the forces that shape our universe. Whether it's through the detection of hidden galaxies, the study of dark energy, or the discovery of entirely new phenomena, the Boötes Void reminds us that even in the emptiest corners of space, there's always more to explore. And with that, we turn our attention to another cosmic enigma, the Eridanus Supervoid and its puzzling cold spot. Now, shifting our gaze to another cosmic mystery, let's delve deeper into the Eridanus Supervoid and its infamous cold spot. This enigmatic region, stretching across billions of light years, has puzzled scientists for decades. At its heart lies a peculiar anomaly, a cold spot in the cosmic microwave background radiation, the faint afterglow of the Big Bang. This cold spot is significantly colder than its surroundings, and its existence challenges our understanding of the universe's structure and evolution. So, what could be causing this cosmic chill? Let's explore some of the most compelling theories. One explanation points to the Eridanus Supervoid itself. As one of the largest known voids in the universe, it contains far fewer galaxies and less matter than expected. This scarcity of matter could cause photons traveling through the void to lose energy as they interact with the gravitational pull of the sparse matter within it. This process, known as the integrated Sachs-Wolfe effect, might explain why the cold spot appears colder than its surroundings. However, while this theory fits some observations, it doesn't fully account for the extreme temperature drop observed in the cold spot. This has led scientists to consider more exotic possibilities. One such possibility is the idea of cosmic texture. In the early universe, as space-time rapidly expanded, it may have developed imperfections or textures in its fabric. These textures could create localized variations in temperature, potentially explaining the cold spot. If this theory holds true, the Eridanus Supervoid's cold spot could be a rare relic of the universe's infancy, offering a glimpse into the conditions that existed just moments after the Big Bang. Another intriguing hypothesis suggests that the cold spot might be evidence of a collision with another universe. According to some multiverse theories, our universe could be one of many, existing alongside others in a vast cosmic landscape. If another universe collided with ours in the distant past, the energy released from such an event could have left a lasting imprint, manifesting as the cold spot we observe today. While this idea remains speculative, it opens up fascinating possibilities about the nature of reality and the existence of other universes beyond our own. The Eridanus Supervoid's cold spot also raises questions about the limits of our observational capabilities. Could there be other anomalies like this scattered across the cosmos waiting to be discovered? As our telescopes and instruments become more advanced, we may uncover more of these cosmic oddities, each offering new clues about the universe's origins and structure. The cold spot serves as a reminder that even in the vastness of space, there are still regions that defy our expectations and challenge our understanding. As we continue to investigate the Eridanus Supervoid and its cold spot, one thing is certain: this cosmic enigma is far from being fully understood. Whether it's a result of cosmic texture, a collision with another universe, or something entirely different, the cold spot represents a frontier of discovery. It invites us to question our assumptions, push the boundaries of science, and explore the unknown. And with that, we turn our attention to another fascinating void, the local void, and its influence on our own cosmic neighborhood. Now, let's turn our attention closer to home and examine the local void, a vast, nearly empty region of space that surrounds our Milky Way galaxy. This cosmic void, stretching over hundreds of millions of light years, is not just a passive backdrop. It has played an active role in shaping the evolution of our galaxy and its neighbors. But how exactly does a void influence something as massive as a galaxy? Let's unravel this cosmic mystery. the local void exerts its influence primarily through gravity, or rather the lack of it. Unlike regions filled with galaxies and clusters, voids contain very little matter, which means their gravitational pull is significantly weaker. This imbalance creates a kind of cosmic tug-of-war. On one side, the dense regions of the universe, like galaxy clusters, pull matter toward them. On the other side, the local void's emptiness creates a kind of gravitational push, causing galaxies on its edges to move away. This dynamic has had a profound effect on the Milky Way and its nearby galaxies, influencing their motion and distribution over billions of years. One of the most striking examples of this influence is the motion of the Milky Way itself. Our galaxy is not stationary, it's moving through space at an astonishing speed of over 600 kilometers per second. This motion, known as the Milky Way's peculiar velocity, is partly driven by the gravitational pull of nearby galaxy clusters like the Virgo cluster. However, the local void also plays a role. Its lack of gravitational attraction creates a kind of vacuum effect, subtly nudging the Milky Way and other galaxies away from its center. This interplay between dense regions and voids has shaped the large-scale structure of our cosmic neighborhood, creating the intricate web of galaxies we see today. But the local void's influence doesn't stop there. It also affects the formation and evolution of galaxies within its vicinity. Galaxies on the edge of the void, including the Milky Way, often exhibit unique properties. For instance, they tend to have fewer interactions with other galaxies, which can slow down the process of star formation. This relative isolation means that galaxies like ours have had more time to evolve independently, leading to the diverse array of stars, planets, and other structures we observe today. In a way, the local void has acted as a cosmic incubator, allowing the Milky Way to develop its distinct characteristics over billions of years. Interestingly, the local void's influence extends beyond just the Milky Way. It has also shaped the distribution of galaxies in our local group, a collection of about 50 galaxies that includes Andromeda and the Triangulum galaxy. The void's gravitational effects have caused these galaxies to cluster together, creating a dense region of space that stands in stark contrast to the emptiness of the void itself. This clustering has had a ripple effect, influencing the orbits and interactions of galaxies within the group and contributing to the dynamic environment we observe today. As we continue to study the local void, one question remains: what other secrets does it hold? Could its emptiness be hiding clues about dark energy or the universe's expansion? Or might it reveal new insights into the formation of galaxies and the cosmic web? While we don't yet have all the answers, one thing is clear: the local void is far from being a passive feature of the cosmos. It's an active player in the grand story of the universe, shaping the evolution of galaxies and offering a window into the forces that govern our cosmic home. With this deeper understanding of the local void's influence, we now turn to another intriguing phenomenon, the KBC void, and its implications for the expansion rate of the universe. As we reach the end of our journey through the enigmatic world of cosmic voids, it's clear that these vast, empty regions are far more than just blank spaces in the universe. From the colossal Boötes Void to the mysterious dark flow, each phenomenon we've explored offers a unique glimpse into the forces that shape our cosmos. These voids challenge our understanding of gravity, dark energy, and the very fabric of space-time, pushing the boundaries of what we know about the universe's structure and evolution. The 25 unexplained phenomena we've uncovered highlight the incredible complexity of cosmic voids. They influence everything from the motion of galaxies to the distribution of matter, and even the expansion of the universe itself. Whether it's the eerie emptiness of the local void or the puzzling cold spot in the Eridanus Supervoid, each mystery invites us to question, explore, and rethink our assumptions about the cosmos. These voids are not just empty spaces, they are laboratories for testing the most fundamental theories of physics and windows into the universe's deepest secrets. But the story of cosmic voids is far from over. With every discovery, new questions arise. Could these voids hold the key to understanding dark energy or the nature of dark matter? Might they reveal clues about the early universe or even the existence of a multiverse? The possibilities are as vast as the voids themselves, and the answers lie waiting to be uncovered by future generations of astronomers and explorers. So, what do you think? Are cosmic voids simply the universe's empty spaces, or do they hold the answers to some of our greatest cosmic questions? Share your thoughts in the comments below, and let's continue this fascinating conversation. If you enjoyed this exploration of the universe's mysteries, don't forget to like, subscribe, and hit the notification bell so you never miss a journey into the unknown. Until next time, keep looking up. The cosmos is full of wonders waiting to be